Here we've got a quadratic sequence and we're being asked to substitute numbers into it. To work out the first three terms of the sequence, so that's going to be when n is 1, n is 2, and n is 3. And we can substitute it in if we like, or we can actually use the table function, which will work really well. So I know I've got n squared here, but I can just treat it as x. Here it is, x, and then squared minus x plus 11. Start at 1, end at 5, might as well. I'm only interested in the first three, 11, 13, and 17. Just to check, without a calculator, if I was to put 3 in, then I'd get 9 minus 3 plus 11, and that would indeed give me 17. Show that this expression does not only generate prime numbers. Well, this one, so far is prime numbers, so we have to find the value of n such that we get n squared minus n plus 11 that we know is not prime. Okay, and we could try some values, 4, 5, 6. Actually, the table function comes in really useful again for that. I think I have to go back and do it all again. But you're going to have to recognize your prime numbers here to some extent. So now I didn't actually look at the fourth and fifth one. I'm going to go up to 15 just to make it a large amount. Okay, and I'm going to go through. So 23 is a prime number. And then 31 is a prime number. 41 is a prime number. 53 is. 67 is. Actually, this generates a lot of prime numbers. 101 is. 121. Well, that's actually a square number. That's 11 squared. So that is not a prime number. Not sure about some of these later ones, but I'm not interested at this point. I can just say when n equals 11, n squared minus n plus 11 equals 121 equals 11 squared, which is not prime. Okay, Marta says odd square numbers have exactly 3 factors. Give an example where it's correct and one where it's not correct. In each case, write down the number and its factors. Well, it's correct in many cases. For example, 9 is equal to 3 squared. And that has factors 1 and 9, and then 3. Not correct. Well, one that jumps out to me is just 1. 1 equals 1 squared. That just has a factor of 1. I think something like 8 squared. Actually, that's going to be quite a large. That's going to be a large one. Maybe 9 squared is a good one. So 9 squared is 81. It has 1 and 81. It has 9. It also has 3 and 27. That one has 5 factors. But in any case, like lots of answers here are possible. Just make sure you find one with 3 factors and one with not 3 factors. Okay, the last part of this. This is a awkward question, I think. It can be done in lots of ways. I'm going to do it in the most kind of rigorous way that could be applied in lots of situations. I'll talk a bit about other ways you can do it. So we've got a number, but we don't know what it is, but we do know that it's a common factor of both of these numbers, 288 and 360, and we know it's a common multiple of 4 and 6, and we know it's larger than 25. We need to find 2 possibilities. I think the first thing is the common multiple, because the lowest common multiple of 4 and 6 is actually 12. So it's got to be a multiple of 12. Let me write that 12 out again. It doesn't quite look right. Yeah, so I know it could be 12, or actually it can't be this, because these are not larger than 25. 36, 48, 60, 72. Do you know what? I think a good shout at this point, before I go into my more rigorous approach is to try some of these. I'm only interested in finding 2 of them. So I could try 36. I could see if 288 divided by 36, yes, it's equal to 8. So 288 divided by 36 is equal to 8. And I know that 360 divided by 36 is just equal to 10. So 36 is definitely a possible answer. Okay, I could do the same with maybe 48. 288 divided by 48. That goes into it. Let's just check with 360. Okay, that one doesn't work because that's 7.5. So I can rule that one out. I don't know how much working would be expected here, to be honest. But at least I think I've given sufficient. Like I've kind of shown where this has come from. I've kind of shown that I've crossed out some less than 25, and then I'm just going to show my working for the ones that do work. So if we try 60, pretty sure that 60 is not going to work. 60 is not going to go into 288. Okay, no chance. So let's try the next one, which is 72. Okay, that's 4. And 360 divided by 72 is equal to 5. So I found another one. And actually, that's not surprising because it's just double what 36 is. So that's 4. And that's 5. And I'm done. Found 2 numbers. And actually, I think these are the only 2 numbers. That is the best way of doing this question. I wasn't going to do it like that originally, but it's like finding that they're multiples of 12, writing down your multiples of 12, and then just seeing which ones work is absolutely valid and probably the quickest way of doing this question. Just going to talk about one other approach that you could use. You could actually try and find the common factors of 288 and 360. Now, in hindsight, I think this is just this is making it more complicated. You could then put these into a Venn diagram, and it's not as bad as it sounds because I can actually use my calculator to get the product of prime factors of 288. So 2 to the power 5 times 3 squared. And I can do the same for 360. 2 cubed times 3 squared times 5. And then what do I mean by the overlap? The overlap is where I've got these common factors. So I can see that 2 goes into both of them 3 times. So I can put it in 3 times, and I can put the extra 2's in with 288. With 3, I've got both of them have 3 twice, so there's no extras. And then I've just got an extra 5 going on with 360. And there's my overlapping one. So I can see common factors or any kind of combination of the middle. So common factors, and this is an approach, by the way, for the highest common factor. For the highest common factor, you could multiply these together in the middle. But there are lower common factors as well. And so 8 would be one, but that's not more than 25, so I could rule that out. 24 would be one, and actually the highest common factor would be 72. And that would actually, I could see that would be a multiple of 12, and that would be another way of doing this question. And if I use 2 times 2 times 2 times 3 times 3, that would give me 36. And that would be a way of doing this question. And it's a kind of a more robust way, because if there were more answers, I could work it out this way. But you might still say that this is still quicker, and I'm probably with you on that. In any case, sneaky question, but hopefully you're happy with that explanation.